Yeah, now we will look at a few more parametric approaches, for, especially where extreme values are involved. Earlier we have looked at computation of VaR as well as expected shortfall, or even a coherent risk measure using the parametric approaches. But especially for modeling the extreme values, because risk management believes heavily in the concept of extreme values beyond a certain amount of losses, as they are called as extreme values. We will now look at how do we use this concept of extreme values, and are there any specific distributions targeted towards the extreme values, and how do we address those kind of distributions? That is what we are going to deal with in this particular session. So to start with, see, why do we need to understand this concept of extreme values? They are primarily like, I look at them as low frequency, high severity kind of distributions, or kind of loss events. Probably a big earthquake in a city like Hyderabad. There is a possible, the frequency of occurrence is very, very less. But in case it occurs, the severity, the kind of damage that it can bring, the kind of financial losses it can bring could be very, very high. So modeling those kind of events is what we call as the extreme value modeling. Right? So very huge, sometimes because of a big financial crisis in a country, or a political crisis, huge markets crash, or even because of natural disasters like earthquakes, floods and cyclones and tsunamis. Because of any of these things, what could happen is the loss can be very, very extreme. Though the probability of occurrence of that loss is very, very limited, the impact of that could be quite drastic. But one of the drawbacks which we would see with such kind of a data is very little data is available. The reason is these kind of events, they occur very rarely, so the data availability is very, very less, and even so many losses might not have even occurred till today, right? Probably there is no guarantee that the loss may not be beyond this at all. Sometimes the new crash may come and the loss may even cross this and come up to here also. So not all data might have occurred till date, and whatever the data that is available also, it is very limited, that I may not be able to create a distribution or create a detailed analysis out of that data. So generally what people do is they come out with a workaround wherein they assume a certain distribution for such kind of a data. Right? There are some kind of distributions which are dealing with extreme values. We will talk about a theory called as extreme value theory, and we will also deal with the distributions called as generalized extreme value distributions, or we will call them as point over threshold kind of distribution, POT, peaks over threshold kind of distributions, as well as generalized extreme value distributions, which are nothing but they are just like a normal distribution or a Poisson distribution or a log normal kind of a distribution, some kind of statistical distribution whose focus is not on the central tendency measures but more on the extreme value measures. Right? Now, just getting ahead into this concept of extreme value theory, this theory will help us in determining the VaR as well as expected shortfall where the focus is not on the entire data. If this is the range of my data set, probably the extreme value theory focuses only on this much area of the data set, which is nothing but the extreme values itself. So that's where the distributions relating to the extreme values, they are not based on the concept of central limit theorem, because central limit theorem, what it says, as the sample size increases, the mean of the sample will approach the population mean. So that is what is the base groundwork behind the extreme value distributions, whereas with the regular statistical distribution. But when we bring in the extreme value distribution, this is what is the statement. Fisher-Tippett state theorem is what we typically call as, not the central limit theorem. What it says is, as the sample size increases, the distribution of these extreme values, the distribution of only these data I take and create a distribution out of them, they follow what we call as a generalized extreme value distribution. The normal shape of the generalized extreme value distribution, the equation for that is something like this: e to the power of minus of 1 plus psi times x minus mu by sigma. You remember, this is nothing but this is one of the calculations which we use in case of normal distribution, right? Standard normal distribution, x minus mu by sigma. So in case of generalized extreme value, it behaves like this: e to the power of minus of 1 plus psi times x minus mu by sigma raised to the power of minus 1 by psi, where psi is not equal to 0. Otherwise you don't have minus 1 by sigma there, minus 1 by psi, it becomes e to the power of minus e to the power of x minus mu by psi. See, we have this is nothing but using the concept of limits. If I apply the limit, if I apply this formula limit, saying if this tends to 0, the numerator, it is like 1 plus x minus mu by sigma into psi to the power minus 1 by psi. This actually, we have a theorem, limit n tends to 0, 1 plus px pn to the power 1 by n. This actually approaches e power p. That's the same logic we are using. This approaches e to the power of x minus mu by sigma. So that's the reason, even if you remember this and say if psi tends to 0, what could be the updated form, or you can remember both of these things. And in this case, we will always see that this kind of a relationship, 1 plus whatever is there in this, whatever is there inside this bracket, that number will always be positive. And in this, we are talking about three important parameters. Mu is a location parameter, more or less equivalent to the mean, but it's not the mean because we are focusing only on this portion of the data, whereas this is the actual mean of the data. So only the mean corresponding to the extreme value, that's where we don't use the word called mean, but we call it as a location parameter. Similarly, a sigma is equivalent to that of a standard deviation, but not the standard deviation because we are focusing only on this part of the data. And psi is called as a shape parameter, or sometimes people use the word as tail index for this. So for different values of psi, we get different shapes of the graph. That is what we will be discussing. If psi is greater than 0, there is one kind of a shape. If psi is equal to 0, there is another kind of a shape. And if psi is less than 0, there is another kind of a shape. And there is a different distribution in each of these things. If it is greater than 0, we call it as a Fréchet distribution. Equal to 0, we call it as a Gumbel. and less than 0 we call it as a viable. But the thing is, in most of the finance applications, we don't see this kind of viable distribution occurring quite frequently. The reason being, okay, wherever this psi is greater than 0, we are talking about heavy tails. Tail is very, very heavy, more heavier than the typical normal distribution like your T or Pareto distributions. When psi is equal to 0, we are talking about the tails, which is a Gumbel distribution, but the tails are more or less in line with that of what is a normal or a log normal kind of a distribution. Whereas if the psi is less than 0, the tails are even more narrower than that of a normal distribution, and it's very rare to find such kind of distribution or applications in the world of finance. So we majorly, whenever we are doing a modeling, we are majorly focused on whether I should take psi greater than 0 or equal to 0. For this, how should I take this? There are 2-3 mechanisms which are being suggested on what should I typically look out for the value of psi. Sometimes if I want to be more conservative in my model or try avoiding the model risk, I generally prefer going for psi greater than 0. Or sometimes I can observe the parent distribution, which is like a whole data. Is the whole data following some kind of T distribution, or is it following a log normal or a normal distribution? If it is following more of a log normal or a normal distribution, the whole data, not just the extreme value. If the whole data is following more of a normal distribution, then I may think of modeling the psi value to be equal to 0. But if the original data is following a T or a Pareto kind of distribution, then I may think of modeling psi value as greater than 0. So that way I can use the information from the original distribution, original parent distribution, and I can use that to model the value of psi. And the other parameters, mu and sigma, whatever are there in this case, all of them I can very well estimate. The mu, sigma, any other parameters that are there, I can very well estimate using the concept of maximum likelihood approach. Right? Alright, moving on to the next. There is another approach. So when we are just talking about what are the various extreme value distributions we are talking about a GEV based, generalized extreme value based distributions, which can end up with a freshet or a Gumbel or a viable kind of a distribution, depending on what is the value of psi. So there is other category of extreme value distributions called as a peaks over threshold kind of distributions. Key thing is, this is primarily dependent on the threshold which we are defining. So there is a threshold value, and we are more bothered about what is the probability of the losses beyond this threshold value. That is how it works, right? It works under the concept, what is the probability. You will have to define one threshold value, and this helps me in terms of understanding what is the probability that my losses will cross this particular threshold value. For this, the underlying distribution need not be normal or log normal. If they are normal or log normal, we can directly use the probability kind of approach and try to find out what is the chance that these values are lesser than this particular threshold value. But whatever is the underlying parent distribution, once I define a threshold value, I can very well try to come out with what is the probability of the loss beyond this particular threshold value. The way it works is, it's nothing but, okay, if I am defining a threshold value of u, the probability of loss, the probability of loss less than u plus x, if I am defining that u is a threshold, given that the loss is more than u, what is the chance that it is less than u plus x? This is what we call as fu of x. Given that the loss is greater than u, what is the chance that it is less than u plus x? That can very well be computed using this formula, f of x plus u minus f of u by 1 minus f of u. And here what this extreme value theory is also suggesting is, if u is larger and larger, means if your cutoff threshold limit is increasing, any distribution, any parent distribution will approach the extreme values, whatever the values that are beyond this threshold value, they will approach what we call as a generalized Pareto distribution. That is what is a very important statement we have to remember. If the u is getting larger and larger, means if the threshold limit is going larger and larger, the number of, if I take the values, the loss values beyond this threshold limit and do a distribution of those particular values, it is very clear that those values will follow a distribution which is called as a generalized Pareto distribution. And that generalized Pareto distribution works like this: 1 minus of 1 plus psi times x by beta to the power minus 1 by psi. The psi is same which we have used in our generalized extreme value distribution. Right? Again the same logic. If psi is not equal to 0, this is what I am using. If psi is equal to 0, this entire thing will get converged into e to the power of minus x by beta. So that's where we are saying if psi is 0, this is what is the expression. If psi is not equal to 0, this is what is the expression. Which means here I don't have 3 parameters. In the generalized extreme value, I have mu, sigma as well as psi. Whereas in the POT approach, I only have 2 parameters, psi as well as beta. So it is using slightly lesser number of parameters compared to the typical generalized extreme value distributions. And this again, psi and beta can very well, psi is the same definition, the tail index which indicates the shape of the distribution, and the other way, the both the psi and beta again can very well be estimated using the maximum likelihood approach. And just as a shape for these POT or generalized Pareto distribution thing, if the normal distribution follows this kind of a shape, the typical Pareto, generalized Pareto, it dips below the normal prior to the tail until the extreme tail, it again goes up, and after that it becomes a linear approximation. So it dips below the tail, it dips below the normal before the tail, and after that again crosses the normal until the extreme tail, and after that becomes a linear approximation. This is how the typical generalized Pareto distribution graph looks like. So even if I don't know the parent distribution is the distribution of the entire data. What I can very well think of is, if the u is increasing and increasing, the distribution of the values beyond that threshold, they will typically approach a generalized Pareto distribution. So deciding that u is a very important. The higher the u, probably it is approaching a GPD quite comfortably, but more u are there, probably means the less data points are available, because the number of actual instances where the losses are beyond this particular value, they might be much lesser and lesser. So Even if the U is very large, probably estimating the parameters also will become very difficult. So it's a trade-off. The U should be large enough so that GPD can be easily applied to it, but at the same time small enough so that I am comfortable in estimating the parameters and I will not lose out the most important information in the process. Right? So these two things have to be considered while getting into the extreme value distributions. So just as a comparison approach, both of them have the same objective. They are more focused towards the extreme values and the distribution of the extreme values. But the only thing is, in POT approach, I am very much based on the defined threshold, whereas the typical GEV approaches, they are based on some extreme values itself. And the other way to look at is GEV requires three different types of parameters to be estimated, whereas this one is having lesser number of parameters, whereas the choice of the threshold creates additional uncertainties, because the more I choose or the less I choose, sometimes the data loss and all these things can definitely occur. So there should be enough care in terms of the choice of the threshold value. So how do I use these formula? How do I use this POT formula using to compute the VaR as well as the expected shortfall? This is the formula typically. Probably it's better that you remember these formulas. To compute the VaR, or we are talking of is U, which is nothing but the threshold limit. The threshold limit generally is set in terms of the percentage. Right, the 1% of the losses. So that is the threshold limit that we are setting. Beta and psi, we are estimating them using the maximum likelihood approach into n by nu. N is the total number of observations and nu is the number of observations crossing the threshold. So n by nu, wherein okay, this is my target threshold amount, beta by sigma, beta by psi. N is the total number of samples, nu is the samples which have exceeded the threshold value, into 1 minus confidence interval. If I want 1% VaR, then probably I will set this as 0.99. And if I want 0.5%, 5% VaR, then I will set this as 0.95. So this is what is the number, minus 1. This is what is the formula corresponding to the VaR. So probably in our exam, or probably in our practical usage, I need the value of mu, which is nothing but the targeted threshold limit. Beta and psi are derived from the maximum likelihood, are estimated from the maximum likelihood approach. These two values are based on our sample size and actual values crossing that particular threshold limit. Using these kind of calculations, we can very well compute what is the VaR in the process, and based on the VaR we can compute ES, because expected shortfall is actually sometimes defined as conditional VaR. What is that? It's an average of the VaRs beyond that. So assuming that the loss is beyond the VaR, so probably sometimes it is defined as the expected value of X given X is greater than VaR. This is the typical way that we define our expected shortfall. I want the average value of those values, where the loss is beyond the VaR value. So from that standpoint, we can use this kind of a formula, VaR by 1 minus psi plus beta minus psi mu by 1 minus psi. This is what will give you the expected shortfall. So probably remembering these and putting them as a part of your Excel spreadsheet will typically give you the calculations per VaR as well as the expected shortfall. Sometimes we may end up with the scenarios wherein I may have to deal with multiple random variables parallelly. For that matter, probably yes, if an earthquake occurs, which is a natural disaster, right, my portfolio returns may fall. But at the same time, this itself can result in stock market crash. Which also could result in the returns going down. Mean these two events actually are dependent on each other to some extent. So I cannot use the typical independence of the variables kind of an approach to model the extreme value distributions, especially when I have dependency between the multiple variables. That is where I have to have a dependence on the Coppola's kind of a model, which we have discussed earlier, especially when we have the dependency between the variables, because this is no more an elliptical distribution, and the correlations will not work, because we have discussed earlier that the correlations between the two random variables will work quite comfortably only if those variables are more or less normal in nature. But here we are talking about two extreme values, right? Extreme value distributions which need not be normal. So all the assumptions relating to elliptical distributions or correlation kind of analysis, they cannot work. So the major focus is on tail distributions itself, which means I have to depend on the Coppola's kind of an approach. We have discussed about extreme value Coppola's. So I will be relying more and more on extreme value Coppola kind of an approach to typically model the multivariate extreme value, multi-variable involved VaR computation or expected shortfall computation, and that too if the variables are increasing more and more. Probably in actual data, getting one or two instances of all the things, all the variables occurring together at random, that would be a very rare kind of an occasion. So from that standpoint, getting the data will be a huge challenge. So modeling multivariable extreme value distributions is more and more challenging itself, though I depend on extreme value Coppola's. It makes the modeling job more and more challenging altogether. So we have to really analyze whether the situation is more of univariate extreme value theory, or we are going for multivariable analysis. Alright. So that's how just a quick brief introduction into this usage of parametric approaches for estimating the various extreme values. I hope basic insight has been occurred in terms of understanding these kind of concepts. Any further queries you have on these lines, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.